last session of today, and the first speaker will be Anna, how galaxies trace large-scale structure ever-shift free.
Hello everybody. My name is officially Anna, no officially Anya. And I'm going to talk slightly not related to Akari, how galaxies trace large-scale structure. And that's the question: how galaxies trace large-scale structure at high redshift, and by high redshift I mean redshift 3. And why we are even asking this kind of questions. Simply because we have even bigger question hide behind this question, namely, how the heck has happened that from what looks like this, which is mostly uniform, except of teeny tiny uncertainties, we got to this, the beautiful structures that we can see on the lower redshift ranges and stuff like that. And all would be nice and fun, to just trace the evolution of this thing, if not for the dark side of the universe. And the problem with dark side of the universe is that it's dominant. I mean, we all know that we can see like very, very, very tiny fraction of the universe. The rest is the dark matter, and the rest is, something, which we call dark energy. So, in order to understand how the large-scale structure evolves from one point to another, we need to understand the relationship between galaxies and the underlying dark matter. And this understanding is the most important at high redshift, and by high redshift here I mean redshift 3. So how we are going to do that? First of all, we are going to use a very relatively easy statistical tool, which is called the correlation function, which in a very essence computes the probability of finding two galaxies or two objects in general at a given distance, and this measuring the probability above the random. It's a nice and fun tool, but it has its requirements. You need really, really good spectroscopic data for that, because you need a good measurement of the redshift. And what I did before, I used the galaxy sample, which is called VMOS Ultra Deep Survey, in short VUDS, which is a really nice sample of almost 10,000 galaxies with the redshift range between 2 and 6, covering 1 degree squared field of view. Which is really, really nice, and compared to other redshift surveys at this distance, at this redshift. Here is the gray area, which shows you the numbers, how the numbers of galaxies in this survey compared to other redshift surveys in this range. And you see we have a huge advantage over everyone else. And that's important yet again. This is a spectroscopic data. We have the data, we have the bright side, we have the galaxies. The second thing, we are measuring the correlation function, but we need to quantify it somehow, and for that we are using the halo occupation distribution modeling, in short HOD, which, long story short, this is a model which has two basic assumptions. First assumption, that if you agree with this assumption, I hope, that the galaxies reside in the dark matter halos, and the mass of the halo depends on the number of galaxies that are inside it, meaning that more galaxies, the more massive halo. I hope if you agree with this, you can create a whole, complicated model, from which you can have the halo mass after the fit into the correlation function. You have halo masses of different kinds. The most important for the stock will be the minimum halo mass and the satellite halo mass. The minimum halo mass is the halo mass for which the halo contains only one central galaxy, and the satellite halo mass is the halo mass for which the halo contains one central galaxy and one satellite galaxy. So above this mass, we have more satellite galaxies inside a halo. Then from this you can derive other parameters like the average halo masses for the given galaxy population, galaxy bias, satellite fraction, etc., etc. For which, again, more important will be the galaxy bias, which tells you how strongly there is a shift between the distribution of the luminous structure and the dark matter structure. So so what we got. First of all, we divided our sample into different luminosity and stellar mass samples of galaxies, and we found that the strength of the correlation, which means that here are the galaxies, here is the increasing luminosity, here is the increasing strength of the clustering. So these are basically the denser environments, which means that the more luminous galaxies tend to be more clustered. The same goes with the stellar mass. The more massive galaxies tend to cluster strongly. Skipping to the large-scale galaxy bias, there are two things that you should look for. Here is going like this. Here you have examples of large-scale galaxy bias at different redshifts. Here is the redshift 0, and here is my results on redshift 3. So you can see that the bias increases with the redshift, but not only. There is also a dependence with the stellar mass. So we have two dependencies overlapping with each other, which is moreover complicating the story. The other thing, which is the stellar masses. As I said, just to remind you, the minimum stellar mass, so these are these greenish points, and at redshift 3 and at redshift 0. And the satellite halo mass, these are these points and this, this line at redshift 0. So this is redshift 3, and again, that's my results. So you can see there is a difference. First of all, the halo masses at higher redshift are smaller than the halo masses that we can observe right now, which means that there is the buildup of dark matter inside the halos, that the structures are growing, basically. That's the first thing. The second thing, there is a dependence with, here is the luminosity. We can observe the same thing for the stellar mass. So here is the increase of the luminosity. So the more luminous galaxies tend to be in the more massive halos. Which arguably there is also the relation between those galaxies. Those galaxies it's different. So this relation is more steep than it is observed on the lower redshift ranges. Third thing from the same plot. You can see here is the ratio between the minimum halo mass and the minimum halo mass for which halo has one central galaxy, and the halo mass for which it has central galaxy and a satellite galaxy. So here this ratio is around 20. Here is the ratio. Here this ratio is around 4, which is smaller. Which means, so here I'm going to wave my hands a bit. So if the halo mergers create the satellite galaxies. So you have two separate halos which are merging. So we have then afterwards we have one halo with the galaxies and the satellite galaxies. So if the small ratio means that there is a lot of recently merged dark matter halos which contains recently merged satellite galaxies, which didn't have time to merge. the galaxies didn't have time to merge inside the halo. Which means that we have high halo merger rate and the small galaxy merger rate. And this changes with redshift. And right now, at redshift 0, we have more or less the same halo merger rate and the galaxy merger rate. Another thing that you can take from this, so we have halo masses, we have stellar masses. Let's compute the relation, the stellar to halo mass ratio between them. And what you can see here is this again are points at redshift 3. This is the model, and as you can see here, for the luminous, more or less luminous, not luminous, but massive stellar mass galaxies and stellar mass galaxies, we are more or less in in agreement with the model, which is all nice and fun. The problem starts here, that we are way off. So these are the galaxies that are more effectively forming stars than we would expect them to form stars, and they are in the less massive halo that we expect them to be. So here's the question. We don't have answer for that, more or less. We can blame feedback. We can blame the fact that in the models we simply do not take into account the fact that there are halos that does not have galaxies at all, and which is called like dark empty halos, and this could be like massive halos, maybe. We simply don't know. But there's also another problem. All this thing is in the far UV band. So I'm observing, the star-forming galaxies in the UV band. So in order to answer the question how galaxies trace a large-scale structure, I'm answering the question how UV galaxies trace large-scale structure. So to answer the question how galaxies trace large-scale structure, the answer is, well, it's complicated because galaxies trace dark matter field in a biased way, but the problem is that at the same time the evolution of the galaxies themselves depends on the position in the cosmic wave, which means from the environment. And the best indicator of the clustering and of the properties of the environment dependence of the clustering is stellar mass, which is shown here. This is a marked correlation function with the marks of stellar mass and luminosity, and the stellar mass is always the better indicator of the changes. I lost my point because of that. No, it's fine. So what I need to better do that, I need a multi-wavelength data, which gives me like the robust stellar masses, and not only I can do, like, for example, through the machine learning, I can possibly make the better classification of the galaxies. I can make a lot of types of galaxies, so the better have the full sense of star-forming data, mostly the obscured star-forming data and star-forming galaxies, and so on and so forth. So I can have like a better picture of what we actually can compute, and I hope maybe data from NEP could serve for this purpose. So maybe this picture would slightly change if I would include the obscured star-forming galaxies. Take away messages, and thank you very much.
Alright, thank you. Any questions to Anna?
Because now it's fun, because now there are many cosmological hydrodynamic simulations.
Yeah.
So I can directly compare your stellar mass halo relation to the predictions from those simulations.
That's great. So we can compare the observation. Yeah, that would be pretty cool.
Yeah, but usually the problem is that they fail at predictions at higher redshift.
This is redshift 3. You can, I mean, they could go sometimes to redshift 10 if I remember correctly some hydrodynamical data. There is some problem with volume after that, but I'm not sure if that's available at redshift 3. I'm more too happy than
So if you go back to the plot that you showed,
yeah,
to compare with the other.
This one?
Yeah. So my point is you can plot just directly from the hydrodynamic simulation to see where it falls, right?
Yeah.
There is clear offset.
Yes, there is a clear offset. Okay, cool.
So in your ratio between the minimum halo mass and the satellite mass, so to interpret the result, it means like there was less galaxy mergers in early universe, and now it became
No, they were less frequent at the time, so they didn't have time to catch up with the halo mergers. So the halo merger were simply faster than the galaxy mergers. Yes. Now it's more or less the same level. I mean, they had time to catch up.
So when you say merger here, does it mean like the mergers between the similar size?
Yes, the major mergers between galaxies.
So any other questions or comments?
Yeah, so the last slide you mentioned that the luminosity and stellar mass have dependence, right? Last slide.
Last slide.
Yeah.
So this one, right?
No. More or less.
This one?
No, more or less. In the maybe summary or something. Yeah.
Yeah.
You mentioned that the observed the luminosity and stellar mass dependence. Is this means there's a scaling relations between these two quantities? Is this a meaning?
The relation between stellar mass and luminosity?
Yeah.
Yeah, there is. I mean, technically, the more luminous galaxies are also the more massive ones, but this is only for what we observe for the not obscured star-forming galaxies. So yeah, there is a relation, but it's not one-to-one relation, and that's the whole point. We cannot simply use luminosity and say, okay, this is the massive galaxy, or say massive galaxies, this is a luminous galaxy, because we simply not every time observe everything there is, and that's why we need like the robust multi-wavelength data for the plastic spectroscopy.
And moreover, what we find here is that this relation depends on environment.
Yes.
Yeah. So last on my curiosity, you mentioned at redshift 3. So this is also possible happen that another redshift focuses.
Yeah, this is happening above redshifts. This is all. This been studied, extensively at the lower redshift and redshift 0, and at redshift 1 with Vipers and everything. We are simply trying to check how far does it go, and how does it change? How does it change with redshift? Because if all of these relations, as I showed you, the bias and the masses and stuff, it's all changing with the redshift. So we cannot simply say, okay, we observed it at redshift 0, and that's how it evolved with time, and that's how the properties are related with each other and with the dark matter.
Thank you.
You're welcome.
All right, any other questions? Then let's thank the speaker again.